Okay, so essentially, let us first revise the last class little bit, and then I will move to today's discussion. So in the last class, essentially we discussed how to find the PMF using CDF, and to find PMF using CDF, we have seen that we will be essentially using the left limit of the function. So left limit of the function at point is probability of random variable taking value less than the number x, less than the number x. And we proved that the Bow theorem gives value of the left limit, which in general may not be equal to capital Fx at that point, because we know that CDF is not left continuous. It is always right continuous at every point, but in general, it may not be the left continuous at the point. Okay, so and we know that CDF is a monotonic function, so it can have left discontinuity at most countably many points. At most countably many points. Uh, yeah, so these things are the special comments regarding different CDF functions of geometric Poisson and Bernoulli case, which what we'll essentially get. So EMF we have defined as the difference of the CDF at that point and the left limit of the CDF at that point. That is exactly PMF. And PMF may not be non-zero at every point. It is non-zero at countably many points in the discrete random variable. And yeah, so these things we know. And we have seen some examples. We have seen certain examples in the case of geometric random variable and those things what we essentially discussed in the last class. We discussed in the last class. Okay. So today class we want to discuss the PMF of the composite random variable So we have a random variable capital X which maps each event to uh, some real number x, where x is some real number. So x, the random variable x assign real number to events, and then we have a function from R to R. Let us say that function is g. So that assigns x to gx. Right. So this composite function gx is a function now from omega to r. So we want to see what is the PMF of this composite random variable. So gx is a random variable because it is defined on the sample space and it is real valued function. So in today's class we want to study PMF of composite random variable, function of a random variable. So here function is g and x is the random variable. So function of the random variable means g of x is again a random variable. So essentially what we are asking here is that we are given the random variable x and x has PMF, and using PMF of x we want to find PMF of y. Right? So how to find PMF of y? So in discrete case it is very simple. So we have a result. We will not prove this result. This is quite simple from the definition itself, that if we have a discrete random variable, if x is a discrete random variable, and we have a function from some interval to R. This is a function from interval to R. This interval contains the range of X, right? So therefore we can do the composite function. Then the probability mass function of the new random variable y, which is basically g of x. So this is a new random variable which we are calling y. So y is a function from omega to r. This new random variable has PMF, which is given by the probability of the event y equals to y. Y is some real number and capital Y is this random variable. So what is the probability of y equals to y event? That is summation of, will find all x such that g of x is y. G of x is this y. G of x is this y. So we'll find probability of those x. Probability of events x equals to small x, x equals to small x, where x is such that gx equals to y. Gx equals to y. So we find all such x. So we're starting with some y. Y is a real number. We'll find all x such that gx equals to y. Gx equals to y. And that x is in the range of capital X. X is in the range of capital X. So we can find the probability of those events. Probability of those events. So we'll see some examples. So the first example is a binomial distribution. We have the binomial distribution. So let random variable x is essentially the binomial distribution for n tosses, and probability of success is p. Probability of success is p. So consider the random variable. Consider the random variable y, which is basically n minus x. N minus x. So we know that n is a fixed number, that is the number of tosses, and so that means that is a constant function. We can consider any real number as a constant function. So it is a constant random variable, and using that constant random variable and another random variable, we can discuss the difference of two random variable. It is also a function. It is also a function which is a random variable. So using this random variable which follows the binomial distribution, binomial experiment, and using that random variable, we have constructed a new random variable y. So question is that find the PMF of this y. So we know that to find the PMF, we need to find the probability of y equals to all possible values in the range of y. All possible values in the range of y. So we know that x is a binomial expansion. So range of x is the number of heads what we are getting, that is either 0 head, 1 head, 2 head, up to n heads. So because we are tossing n times, so all possibilities are 0, 1, 2 up to n. 0, 1, 2 up to n. So what will be the range of y? That is n minus all these numbers. N minus all these numbers. So we know that n minus 0 is n, n minus 1 is n minus 1, n minus 2 is n minus 2, and so on. The last one is n minus n is basically it is 0. It is 0. Right? So these are the all points in the range. These are the all values of the range of this random variable. Y. So now for each of this value, we need to find the probability of y equals to each of this number. So for that, so that means let us take k to be any integer in range of y, which is basically 0, 1, 2 up to n. 0, 1, 2 up to n. So if you take any integer between 0 and n, then what is the probability of the event y is equals to k? That we need to find. Probability of y is equals to k, which we need to find. And what is our random variable y? Our random variable y is n minus x. That is n minus x. So let us substitute it here. So that is probability of n minus capital X equals to k. Right? Because y is n minus x. Y is n minus x. And then we know that n minus capital X equals to k. That means capital X is equals to, so x we can take on the other side. So capital X equals to n minus k. So that is probability of capital X equals to n minus k. N minus k. So now we know that what is x? Capital X is essentially the binomial random variable b and p, and we know that probability of the binomial expansion p of x equals to k is basically nck. Probability of success power k. Probability of failure, that is q, which is 1 minus p power n minus k, right? But now here instead of k we have n minus k. So when we substitute this, we get nc. So k is n minus k. So we have n minus k here, right? And then we have p power n minus k, 1 minus p power n minus k, n minus k. Okay, so now if you simplify, we know that using the Pascal triangle, n minus k is equals to nck. So this is actually nck, and then we know that this is as it is, p power n minus k, but this term n minus k will become 1 minus p power k, 1 minus p power k. So now if we compare this term with the binomial expansion, then the first term is as it is. The second term is, instead of p power k, it has become p power n minus k. And the third term, instead of 1 minus p power n minus k, it has become 1 minus p power k. So if you want this term in terms of binomial expansion, these two terms we need to switch. So that means it will become nck 1 minus p power k, p power n minus k, So what has become is, this is also a binomial expansion, but now the role of p is being replaced by the role of 1 minus p. So this is a PMF of the binomial random variable of n tosses, but instead of probability of success is p, now probability of success, which is in terms of power k, is 1 minus p, right? So that means, what is this PMF? This PMF is PMF of the new variable y, So therefore y is the random variable which follows binomial distribution with n tosses, and probability of success is 1 minus p. So p is a variable. P is any number between 0 and 1. So therefore 1 minus p is also any real number between 0 and 1. Okay, so that is regarding this example. We have found the PMF of the new random variable, which is a composite random variable. So the next example is, we have the normal distribution. So let random variable x follows the standard normal random variable, that is n01, and we have the function gx, which is defined to be the sine function. So sine function means it is -1 if x is negative. It takes value 0 if x is equals to 0, and it takes value 1 if x is strictly greater than 0. If x is strictly greater than 0. So again, what is the question? Question is that we need to find the PMF of the random variable g of capital X. G of capital X. Okay, so so what is the first step? Again, the first step is finding the range of new random variable. So here, the new random variable is y equals to g of x, and the range of y is essentially the range of g, right? The range of g is -1, 0, and 1. That is -1, 0, and 1. -1, 0, and 1. So we need to find for each this value y, we need to find probability of capital Y equals to each of these. Probability of capital Y is equals to each of these. So let us first find probability of random variable y is equals to -1. Probability of y equals to -1. So what is probability of y equals to -1? That means we have probability of, so when capital Y becomes -1, capital Y becomes -1, that means capital X takes values in this interval, right? So that means x is less than 0. X is less than 0. So probability of y equals to -1 is essentially probability of x is less than 0. And what is capital X? Capital X is the standard normal random variable with mean 0. This is mean, mu, and this is sigma square, which is basically variance. This is variance. Okay, so let us recall the n01. So what is n01? N01 is represented by the function fx, which is essentially 1 upon root 2 pi e power minus x minus mu square, but mu is 0. So that means it is minus x square divided by 2 sigma square. Sigma is 1, so that means it is 2. It is 2. Right. So this is our standard PMF of n01, and we know that this function is symmetric around y-axis. Symmetric around y-axis. So that means the probability of x less than 0 is same as probability of x greater than 0, right? And since it is a continuous random variable, it is also continuous random variable. Probability of x equals to 0 is 0. Probability of x equals to 0 is 0, right? Because the area of a single point is 0. Area of the single point is 0. So that means probability of x less than 0 is half the total area, and we know that area of this probability mass function is 1. Area of any probability mass function is 1. So that means this is half, and similarly probability of y equals to 1, which is probability of x greater than 0, is again half, because of the symmetricity of this random variable, the PMF of the random variable, and as we mentioned earlier, probability of y equals to 0 is probability of x equals to 0, and probability of x equals to 0 is essentially 0. So reason is that this random variable is continuous random variable, so it doesn't have the left discontinuity at 0. So therefore, the PMF is 0. The PMF is 0. So for all these three values, we have found the probability of y equals to -1. So this is what this is essentially Fy at -1. Right? This Fy at 1, Fy at 0. So we found Fy at each of these 3 points. So that is essentially the PMF of Gx. PMF of Gx. PMF of Gx. So in this case, it is easy to find because our random variable is continuous random variable. In the last example, it is a discrete random variable. This was the example of a discrete random variable. So in general, is there any method which we can use, simple method to find the PMF of the composite random variable? So let us discuss that shortcut method. To find PMF of the random variable y equals to gx. So, so there are very nice examples given in the book of mentioned in CIF of authors. So there are two authors of this book, that is Popolis and Pillai. So in this book, very nice examples and methods are given. So one of the methods which we are discussing is to find the simple method of finding the PDF. So what is given? We are given the random variable g of x. G of x. So what we will do is we will first find. We shall first find all the roots of y equals to gx. So that is essentially this thing. That is essentially so this is essentially finding all x such that gx equals to y. That is finding all x such that gx equals to y. But here it was discrete random variable. But in general, the random variable may not be discrete. But the method is same. We are going to find first all the roots x, of basically y equals to gx. So y is what? Y is the real number in the range of y, range of random variable capital Y, and for that we will find all the real numbers x such that y equals to g of x. Right. So that is basically we have y equals to g of, let us say, x1 is first root, x2 is second root, xn is nth root, and so on. So we know that depending on whether our function is injective or not, or bijective or not, we will find whether a single root or different values of x. Right? If the function is injective, we get a single root, we get several roots. right? Depending on that. So now using that we have found all the roots. So these may be a finitely many elements, it may be infinitely many elements, Then using these all roots, then using x1, x2, all these roots, we get fy of y, that is essentially the CMF of the random variable y, that is exactly fx at x1, fx at the first root, divided by the derivative of the g function at x1 and its modulus. Right? This is the first term. Similarly, if there are two roots corresponding to y, then we'll get fx of x2 divided by x dash by x2. If only one root is there, then only one term will be there. If there will be two roots, then up to two roots. And then this formula will go onwards, depending on how many roots are there corresponding to each y, and that depends on what is g. That depends on what is g. So let us take one special case of this. So first case is we have the random variable which is in the linear form, form. So let y is essentially ax plus b, where a is non-zero number, a is a non-zero real number, and b is also real number, a and b are real numbers. So we want to find so what is our gx here? Our gx is essentially ax plus b. So x is a random variable and gx is also a random variable. Okay, so so y is gx. So we want to find the PMF of y corresponding to PMF of x using so if you know the PMF of x, we can find PMF of y using this formula. So let us find out what is this formula for this particular case. So for that we need to find the derivative of g. So gx is ax plus b, that means g dash x is a. For every x, for each x. And so in this case, what is and what are the roots we get here? Note that gx is equals to 0 gives ax plus b is 0, x plus b is 0, and yeah, so gx equals to y, right? We need to find the roots of equation gx equals to y. So gx equals to y, gx is ax plus b is equals to y. So we need to find all possible x such that gx equals to y. So in this case it is easy because it is a linear equation. So we can derive this equation y in terms of x. So we get y minus b, and since a is non-zero, that is the reason why we are taking a is non-zero. So since a is non-zero, we get this divided by a. So we got corresponding to each real number y, we get only one choice of x, that is x1. So therefore the formula in this case is, since we have only one root, the formula in this case is up to this. right? So that means what is fyy. So did I write fyy? Yes. So that is fyy is equals to, what is the formula? Formula is fx at x1 divided by the modulus of the derivative at x1, derivative of g at x1, right? And then we know what is x1 here. What is x1 here? We also know what is the derivative here. That is a, right? So modulus of a we can take outside. So that is 1 upon modulus a, that is this term, and the numerator is fx at x1. Fx is this function. No, sorry, fx is the PMF of the random variable x. So that is as it is. We need to just substitute x1. X1 is y minus b by a. Y minus b by a. So what does this represent? This represents that if we are given the random variable x, which may be binomial or geometric or normal, whatever, and if we are defining the new random variable, which is a linear random variable, right, using the linear equation, then the PMF of this linear random variable is essentially can be found using the PMF of the given random variable, PMF of the given random variable x, right? So we have found this formula now. So case 2 we'll discuss later. Let us first take some example. So the first example we are we are considering is a normal random variable. So let's take the first example. So if if our random variable follows the normal random variable with mean mu and variance sigma square, and if a is a non-zero number, and uh, and b, a and b are real numbers, and consider the new random variable. So and consider a new random variable. Basically we are going to take the first case, that means our random variable is linear random variable. So let us take it is y equals to ax plus b. The condition we assume is a is non-zero. Right? A is a non-zero number. So then our goal is to find find fy. So basically we want to find the PMF of the new random variable y. So solution is quite simple. So from the above formula, we know that fy at y is essentially 1 upon modulus a times fx at x minus b by a. That is exactly this formula which we have derived. Okay. And then we know what is our random variable. Given random variable is normal distribution, and we know that normal distribution with mean mu and variance sigma square has the formula 1 upon sigma root 2 pi exponential e power minus x minus mu square divided by 2 sigma square. So you need to remember all this formula. You need to remember this formula. If you remember this formula, we can use it here. So in this formula, what we need to substitute? Instead of x, we need to substitute x minus b by a. So instead of x, we need to substitute x minus b by a, and we need to divide it by modulus a. So let us write down this. So we have 1 upon modulus A times sigma root 2 pi, sigma root 2 pi times e power minus, instead of x we have x minus b by a minus mu square divided by 2 sigma square divided by 2 sigma square. Right, so let me write this in bracket so that we can remember also. Okay. Okay, so now this this thing we need to simplify. We need to simplify because now here the variance was sigma. So here the variance has changed. The variance has changed. So we need to convert this formula in this type of equation, in this type of equation, so that we can find what is the corresponding mu and sigma. What is corresponding mu and sigma? So what is the corresponding variance and the mean? What is the corresponding variance and mean? So if you simplify this, what we get? We get this equals to 1 upon mod a sigma square root 2 pi, and then we need to take the LCM. So that is minus of x. So yeah, so minus of x minus b times a mu square, and the denominator is a square that we can take in the denominator, so it will become a square sigma square, right? So a square we have taken in the denominator, it will become a square sigma square. So now what is this formula? This formula is in this form, where our new mu is this one, right? And our sigma, which is coefficient of 2, has become a square sigma square. It has become a square sigma square. So that means this is essentially, therefore y is the random variable, which is again normal random variable because it is following the random variable formula of normal distribution, where the mu is b minus b plus a mu, right? Because minus we need to take common, and then in the denominator we have the variance 2 times sigma square, where sigma is this one, a square sigma square, a square sigma square. So whatever sigma we take in the beginning, whatever sigma we take in the sigma square we take in the beginning, that variance is now changed in this new random variable as a square sigma square, where a is coming from this linear equation of the random variable, Okay, so we can see that whenever we take the, so here we have taken the normal distribution, but when we take the linear random variable, so the normal distribution has become the normal only the mean and variance has changed. Mean and variance has changed. Right. So the linear random variable is actually not changing the type of the random variable. The normal remains the normal. Normal remains the. So, so you can check that this is this also happens for the other random variables. Just try to verify that. So here we have considered the normal random variables. So now we have the one discussion we want to do with respect to the normal random variable. That normal random variable with mean 0 and variance 1 is called the standard random variable. Called the standard random variable. Standard random variable. And we denote the CDF. We note the CDF of the standard random variable by nx, by the function nx. So that means what? That means if x is the random variable n01, then nx, that is basically its CDF, that is probability of x less than or equals to x, x less than or equals to x, and since it is a continuous random variable, it is left continuous, and therefore probability of x equals to x is 0. So probability of x less than or equals to x becomes probability of x less than x, okay, because x is continuous. X is continuous at every point. At every point. So what is this probability function? So we know the formula of standard normal distribution. We have already mentioned above. We have already mentioned above. That is 1 upon root 2 pi e power minus x square by 2. E power minus x square by 2. So this formula, using this PMF, we can find the CDF from up to x, and therefore it is nothing but the integral minus infinity to x up to x of function 1 upon root 2 pi e power minus t square by 2 dt, right? So now these integrals, such integrals we have came across when in mathematics 1 course and mathematics 2 course. So this type of integrals are essentially the improper integrals, and so we studied improper integrals in the M1 course, and in M2 course we have come across this in when we studied the Laplace transform. So this integral is related to the gamma function. We find the gamma half is root pi. There we use this integral, but we cannot find this integral. Without finding the integral, we have used this to find the gamma half is root pi. Gamma half is root pi because this function does not have antiderivative. Right. So this function does not have antiderivative, so we cannot integrate it directly. So what we use is we can use the approximate value of this integral, and such a approximation is given like a logarithm table. We have a table of the standard normal distribution function at different values. We have the values already known, and it is given in most of the books, and even you can find on internet. So using this table, we can find different values of nx when x is positive, right? Again, we are using the normal distribution, standard normal distribution function is symmetric around the x-axis, So if you take any positive real number, then n of minus x is essentially probability of x less than or equals to minus x, by the definition of CDF, and that is essentially 1 minus probability of x less than or equals to x, because x is symmetric around y-axis. So since it is we know that it is symmetric around y-axis, so integral up to minus x and x, the total is 1. Right. So anyway, so So this is coming from the total integral of the probability function is probability mass function is 1, and so that is what we are using here. So and what is this value? This value is essentially nx. This value is essentially nx. This value is nx. So this is 1 minus nx. 1 minus nx. So if you know nx, we can find n minus x by just subtracting it by from 1, subtracting it from 1. So using this, we can find, if you know all the positive values of n, we can find all the negative values of n. All the negative values of n. So using this, we can find several probabilities. So let us have a remark. So since we have this the table of standard normal distribution function, but the given normal variable, it may not be standard or not. It may not be standard. It may also be standard. It may not be standard also. So first we need to convert it into the standard form. We need to convert it into the standard form, and we know that the linear random variable doesn't change the behavior of the random variable. So linearization doesn't change the behavior. So let us start with any general random variable. So let x is n mu sigma square, and consider the linear random variable, which is y, that is x minus mu by sigma. So basically we are using the scaling and translating, right? Shifting and scaling. So we want to find what is the PMF of y in terms of PMF of x. So then by the above case 1 formula, we get, so note that this is also a linear random variable. So what we get is we get fy is essentially fx at x1, because this is a linear function, linearization. We have x1 divided by derivative of g dash at x1, where, so what is x1 here? So x1 we get when we take this equals to y. So this equals to y. That means y sigma plus mu is x. Right? Y sigma plus mu is x. So that is x1. X1 is mu plus sigma y. And what is the derivative? So this is our g. This is our g of x. So derivative is so mu and sigma are numbers. So derivative of mu by sigma is 0. Derivative of x by sigma in terms of x is 1 by sigma. G dash of x is 1 by sigma. Okay, so this is y, right? This is fy at y. Okay. So now we got the formula. So what is this? In this case, fy of y. In this example, fy of y is fx at x1, that is mu plus sigma y, and divided by modulus of g dash x. But since sigma is, we are taking is positive, so it is 1 by sigma. Okay, so what we get now? What is fx? Fx is the PMF of this random variable, n mu sigma square. So what is the PMF of n mu sigma square? We already know, that is 1 upon sigma root 2 pi. So this is its PMF. any question?
Hello, sir.
Yes.
So sigma should be in the numerator, no? So because it's
Sigma.
fx by g dash x, and so g
Just
dash x is 1 by sigma.
yes, yes, you are right. So I did mistake. Yeah, thanks for the correction. You are right. So yeah, so that is correct. Otherwise, we will have some mistake in the next computation. So you are right. So since we are dividing by 1 by sigma, sigma must be in the numerator. Correct. Yes. So now we have sigma in the numerator times fx, and fx follows the standard. Fx follows the normal distribution with mean mu and the variance sigma square. So when we substitute it, that is 1 upon sigma square root 2 pi and e power minus x minus mu square. Now x is our this, we need to substitute this quantity. So that is mu minus mu plus sigma y minus mu square This is our x now, and divided by 2 sigma square. So as you mentioned, sigma must be in the numerator. So now we can see that sigma will cancel, and what will remain is mu will also cancel here. It will also cancel, and sigma square we can take common here. So sigma square will cancel with sigma square. So what will remain is 1 upon square root 2 pi e power minus y square divided by 2. And this is, we know that this is this is the PMF of the standard normal distribution function in terms of variable y. So variable is changed from x to y, right? So this is a n01. So therefore, y is essentially the normal random variable with mean 0 and variance 1. So what we have done, let us recollect again. So we started with any random, we started with a normal random variable with arbitrary mean mu and arbitrary variance sigma square, but we use this this random variable y. So using x, we constructed new random variable y in terms of mu and sigma, given mu and sigma. So this new random variable y follows the standard normal distribution. So what is the outcome of this? Let us write in the remark. So in the previous example, if we compute probability of CDF at x, so CDF at x is essentially probability of, so x less than equals to x, that means x minus mu less than equals to small x minus mu, and if you divide by sigma is positive number, so this is less than equals to sigma, right? So whenever x is less than equals to x, that means the events all the points w, so that xw less than equals to x, we have this random variable at w is less than equals to this number. So therefore this event is same as this event. So probability of this event is same as probability of this event. And what is this random variable? That is y. That is our y. So y is less than equals to x minus y by sigma. And this is our standard random variable. This is our standard normal random variable. So we have denoted this CDF of standard normal random variable by capital N. So that is capital N evaluated at this point, x minus mu by sigma. Right. So whenever this point is positive, we have the CDF is, we can find in terms of standard normal variable. So we can use this table. and we can find probability of any normal random variable, which may not necessarily be standard normal variable. So let us see one example. So let x be any normal random variable. Any arbitrary random variable which not necessarily be the standard. So with parameters mu and sigma square, So we need to find the value of probability of the event mu minus sigma less than equals to x less than equals to mu plus sigma Okay. So we need to find the probability of mu minus sigma less than equals to x less than equals to mu plus sigma. So we know that this event we can write as in terms of two different events, that is probability of the event x less than equals to mu plus sigma minus probability of x less than mu minus sigma, and then we can use this computation that probability of x less than equals to x is this quantity n of x minus mu by sigma, so that is essentially n of mu plus sigma. So what we do is, whatever x is given, we need to subtract mu and divide by sigma. So mu plus sigma is x here. So mu plus sigma will subtract mu divided by sigma minus p. Again mu minus sigma we subtract mu divided by sigma, capital N. So now if we find this quantity, that is sigma by sigma, so that is n of 1, sigma will cancel out, and minus this is n of minus sigma by sigma, that is minus 1. So n of 1 is positive number, n of minus 1 is negative, and then we know that n of minus x is, whenever x is positive, n of minus x is 1 minus n of 1. So that is n of 1 minus n of 1. So that is 2n1 minus 1. So we need to find n1 now, that is the value of the standard normal random variable at x equals to 1. So we will use this table, which you can find in the books or even on the internet. So whenever x is 1, the value of the standard random variable is 0.8413. Minus 1. So now if you multiply this by 2, we get multiple of 13 is 26, and 84 is 164, and this one here. So minus 1, so that is essentially 0.6. I think this is 84 multiple is 168, so that is 6826. Okay. Right, so we can use this this table to find the different values. Okay. So using the standard, what we have seen is we can find different probabilities. We can find different probability of different events of any general normal random variable using the standard normal random variable table. Okay, so this is regarding the first method which we have discussed. That is the whenever our random variable given, new random variable is a linear function of the given random variable. Now next we want to discuss is the is method 2. That is whenever we have the square function like parabola. So that is method 2. So in which we have the random variable given new random variable as 2ax square, where a is a, we can take non-zero or we can take positive number also. So here, what is our function? Our function of random variable x is ax square, So therefore, its derivative is essentially 2ax, is 2x. And what is our method? Our method is we need to find all the roots y such that y equals to gx. So now y equals to gx gives y equals to ax square. So this is the equation of parabola where a is positive. So we need to find all possible x in terms of given y. So it is clear that so what is y? Y is a real number in the range of random variable capital Y. So since a is positive, this number is positive. So it is clear that if y is less than equals to y is y is less than 0, then y equals to ax square has no roots. Right? No roots in terms of real numbers. Because the range of random variable x is r. We need to find all possible small x that y equals to ax square. For y greater than equals to 0, we have two roots. So basically 0, they are identical, but essentially the case is y is strictly greater than 0. Roots we already know. It is easy to find that it is square root of y by a, positive root, and negative root. So here we are dividing by a, so a must be either non-zero, and we are taking positive because we are taking square root. So now we apply the shortcut method. So here we can see that corresponding to each y, we are getting two different roots. If it is 0, they are identical, but if it is positive, they are two different roots. So therefore, by the shortcut formula, so we get f of capital Y at y is essentially, now we have two roots, x1 and x2. That means there will be two terms, fx at x1 divided by g dash at x1 plus fx at x2 divided by g dash at x2. So we have two roots. Now we can substitute it. So we don't know what is fx. That depends on which random variable x is given. But roots we know, and we know g. So let us substitute that. So that is root y by a divided by g dash is 2ax. G dash is 2ax. So let us substitute 2ax here. So that is 2ax1. Its modulus, and x1 is root y by a. Right. So since a is positive, this is also positive. So modulus we are not writing. plus fx at the other root, which is minus root y by a, and divided by, now the second root is negative, but its modulus we need to take positive, so again it is 2a root y by e, 2a root y by e. So this is the case when essentially y is negative for the part, y is non-negative, right? Okay, so let us take one application of this. So let me show open some. So we want to see some example of these. So I need to open one more PDF. Okay, it's 15 only, no 16. So, so this is the case when we have the quadratic equation instead of the linear equation. So there are many equations which comes when we see different subjects. So one of the topic we have studied is power in terms of voltage across resistor, voltage across resistor. So let us take that example. So the voltage across a resistor is a random variable let us call it E, right? So usually we denote by random variable capital X, but here we are called that is uh, uh, voltage across the resistor, that we are denoting by small e or capital E, whatever notation you are comfortable. So we will denote by bold letter to represent the random variable. So we call this random variable is a uniform random variable between 5 and 10 voltage, between 5 and 10 voltage. So E is the uniform distribution, uniform random variable over the interval 5 to 10, over the interval 5 to 10. So we shall determine the density of the power. We want to determine the density of the power. So let us say the power formula, if you recall, that is E square by the resistor, which is constant. So R is 1000 ohm, and so basically this is dissipated in R. So what is the question? Question is, we want to find the PMF of this random variable W, and the random variable W is in terms of the random variable E, And E is the uniform random variable over the interval 5 to 10, So we already know the information about the random variable 5 to 10, and we can easily see that this formula is essentially the quadratic formula. It is it is of the form ax square, right, where a is the constant 1 by r, which is 1 by 1000. So note that here, if we compare the random variable equation W equals to E square by R with Y equals to AX square, we get So what is A is, yeah, so we get Y is W, X is E, and E is 1 upon R. And what is R? R is given to be 1000. Value of R is 1000. All right, so that means this is 1 divided by 1000. So E is 1 divided by 1000. So that we got. So let us find out. So we know the PMF of the uniform random variable, right? So since E is uniform random variable over the interval 5 to 10, we get its PMF as, what will be its PMF? PMF is basically fx of x, that is fe of E, right? Bold E. So that is basically it takes value 1 upon b minus a, where the interval is a to b. So 1 upon 10 minus 5, that is 1 upon 5, 1 upon 5, where the variable is in the interval 5 to 10. It is in the interval 5 to 10. Okay, so by the, now since our function is a quadratic function, right? It is a quadratic function. We'll be using the method 2 shortcut formula. So therefore, using the shortcut formula of method 2, using the shortcut formula of method 2, what we'll get is, we'll just substitute it at two things. But now we know that the value of E cannot be negative. The value of E cannot be negative. So since this has two roots, but the other root is essentially 0, its value is 0. Its value is 0. So what we get is, we get FW, random variable W at W, is 1 upon 2a. So let us go back to the formula which we derived. So what is the formula? Formula is the negative is 0. So that we will not keep. We'll take only this term. So this term is 1 upon 2a square root y by a. But y variable is now w variable. So that means 1 divided by 2a root w by a, root w by a, and then f of the given random variable at the root which is square root w by a, square root w by a. All right, and then we know the value of fe, that is 1 by 5 if our variable belongs to this interval. Our variable belongs to this interval, and we know that a is, what is the value of a? That is 1 by 1000. That is 1 by 1000. So let us substitute all this value. Let us substitute all this value. So then what we'll get, this value is essentially 1 divided by 2 root a root w uniform rendered variable at 1 to 10, 1 to 10, that is fe, evaluated at square root w by a. A is 1 by 1000. That means we get 1000 w, 1000 w, right? 1000 w. And now again a is, we need to substitute 1 by 1000. So that is essentially square root 1000. It is square root a, and divided by 2 root w, and we have found the uniform random variable. Value is 1 by 5. Value is 1 by 5. But now we need to find the corresponding interval. Right. So to find the corresponding interval, we need to take this value in the interval 5 to 10. This value in the interval 5 to 10. So that is 5 less than equals to, the value of this is 10 root 10w, less than equals to 10, right? So this is square root 1000w, and then we divide by 10 root 10. So this interval becomes 1 by 2 square root 10 less than equals to square root w less than equals to 1 by square root 10, right? And then we are actually looking for the interval in terms of w, so we need to square it. So we get 1 by 40 less than equals to w less than equals to 1 by 10. Right. So what is the final answer? Final answer is we found the PMF of new random variable, that is this one, when our w belongs to this interval. W is in the interval 1 by 40 to 1 by 10 to 1 by 10. So this is just an application using our known formula of the power in terms of volts. Okay, so let us take one more last example before we stop in today class. So we want to introduce a Cauchy random variable. So we have a random variable with given PMF. So let x be a random variable. With with the probability density function, which is given as fx x equals to 1 upon pi 1 plus x square, where x is a real number. So we say that x is a random variable with this probability density function. Then this random variable we call the Cauchy random variable. So like standard normal distribution, we have certain probability density function. For the geometric, we have certain density function. This is a density function of some random variable. That random variable we are calling the Cauchy random variable. So what is the question? Question is find the PDF of 1 upon x if it exists. So here here we are given the function random variable 1 upon x. So this is not linear, this is not quadratic also, but we have the shortcut formula, so we are going to use the shortcut formula. So note that here our random variable y is g of x is essentially 1 upon x. So therefore the function is 1 upon x, so its derivative will be minus 1 by x square. So we know that derivative is minus 1 upon x square. And yeah, so what is the shortcut formula? So I have so we discussed the shortcut formula, but we have not mentioned that we can use the shortcut formula provided the denominators are non-zero. Right? Because if g dash of x1 is 0, we cannot divide. Right? So therefore, all these denominators must be non-zero to apply the method. So this method works only for those y for which x, the derivatives of g dash are non-zero. So we know that derivative of g dash minus 1 upon x is non-zero if x is non-zero, So that means we can apply the shortcut formula for all those points for which x is non-zero, for all those y for which corresponding x is non-zero. So let us find out what are the possible x. What are the possibles x? So given real number y in R, which is y in R, take x1 to be 1 upon y if y is non-zero, right? Because our relation is y is 1 upon x, that means x is 1 upon y, So given y, we can always find a real number x, so that g of x is y if y is non-zero, So all non-zero points, first we'll find what is f, what is the fy, So therefore fy at y is essentially fx at x1 divided by g dash at x1, and that is essentially fx at 1 upon y, divided by the derivative. Derivative is minus 1 upon x square. That we need to evaluate at 1 by y. So g dash at 1 by y. So if you substitute this in the fx formula, fx is this function. So if you substitute 1 upon y here, we get y square plus 1, and y square will come in the numerator, right? So what we get is essentially we get y square divided by pi 1 plus y square, and divided by this quantity, that is y square, because substituting 1 upon y in minus 1 upon x square is y square, So essentially what we get is we get 1 upon pi 1 plus y square if y is non-zero, And what is this distribution function? That is essentially the given distribution function in terms of new variable y, right? So we know that this function is continuous function. So if you change its value at a single point, it will not change the area. So define fy at 0, that is exactly value of this at 0 is 1 upon pi. So if we define fy to be this function at 0, our fy will become continuous function. And therefore y follows the Cauchy random variable in terms of y. So even though we have taken the inverse random variable, in this case we are getting the same random variable. It is not necessary that every time we get the same random variable, but for this particular example, we are getting the same random variable. Okay, so let me stop here. So if you have doubts, you can ask now.